All right. Okay. This is going to be distracting, but I'll try. So yes, hello, welcome. It's good to be here in Campina Grande. Grande or Grande? Grande. Does it matter? Okay. And I'm happy to share this work. It's a different take on the usual things I do about Newton. So the message here is going to be sort of hidden in the forest somewhere, and the question is, do you see the forest or do you see the trees? And like so many things that happen in the history of science, sometimes our task is just to unravel things, but sometimes our task is also to throw everything back in. And it's a little bit of a play. We're gathered here today, in a sense, as a learned society. And the scenario that I will talk about occurred in the mid-eighteenth century. So we're talking about 250, 270 years ago, the events occurred in a setting I can only imagine not too different from this, except like what was going on. More fortunate because we have women who participate in these settings, unlike what was going on then. We have a diversity of people, unlike what was going on then, and so on. There are some marked differences, but what we're doing today and this week and in other settings like this is precisely what was going on during this period. We tend to sit from our perches in the 21st century, and we look at science and the history of ideas, and we try to make sense of them. And when we're teaching history of science, and maybe even science education and nature of science, we tend to focus on the science itself. And I'm going to try to persuade you to think about something else that's going on through this scenario. So the title itself comes from the fact that with Newton, it wasn't as if Newton wrote the Principia and then it was done and everyone just accepted it. There was a huge debate after the publication of the first edition of the Principia and the last edition of the Principia, the third. There was a huge debate, and it took some time before Newton's physics was actually accepted into what Kuhn might call normal science. That's what we're going to explore. All right. So it's going to be something like this. I'm going to talk a little bit about the lunar theory, but lunar problem, but other problems that went on. I'm going to talk a little bit about metaphysics, although I'll probably never say the word metaphysics again from here on. But I really want to talk about the rise of learned or academic societies. What I'm doing is, first of all, not complete. So you should know that. I don't know if it ever will be completed, but that's the nature of our work. I think what I'm going to talk about is relevant to history of science. I hope it's relevant to the history of science. I'm a philosopher of science who comes to philosophy of science through history of science. So it's relevant to the philosophy of science. It's certainly relevant to questions dealing with progress in science, which I think is important to science education and nature of science studies. It's important for reasoning and argumentation. So I think what I'm working on here is cross-disciplinary to be sure, maybe even interdisciplinary, right? It's interesting for those who actually are doing science because the problem I'm going to be talking about is what's often called the classical n-body problem, right? I think in argumentation studies, it forms a nice case study, and even the study of rhetoric might come in. I don't know a lot about rhetoric except from what's in the media these days, but it's rhetoric as a persuasion, a means of persuasion. There's a fair bit of rhetoric that actually takes place in historical studies of science. So I'm going to start actually not in the 18th century, but actually in the 17th century. And we see in the 17th century the Royal Society of London. I think it got its charter in 1660. I think that's correct. The Paris Academy was in 1666, shortly thereabouts. So not long after that, we get the St. Petersburg Academy, the Berlin Academy, and then a whole bunch of them start going. Right? But for our purposes, these are the four places where a lot of activity is going on. And I know I'm excluding here. There were some academies in Italy, for instance, that were quite productive and so on. But for this story, these are and these were really the four big ones. I put in there Philosophical Transactions of the Royal Society, which the Philosophical Transactions are still being produced. The Royal Society still produces a fabulous journal, actually. But this is also the start of journal publications. It was in this period. Right? In 1672, Newton published his nice little paper on lights and colors. Sibeli and I have argued about this paper before. It marks the start of not only presenting one's work in a conference or a meeting, but it also marks the start of academic discourse through journal publication. Right here. Okay. I keep calling them learned societies, academic societies, academic groups, call them what you wish. What do we know about them? Well, first of all, they're multidisciplinary. So one change from what we have today is, by and large, a lot of our work tends to be done in silos. Much of our work is done with colleagues who are in the same discipline. Right? So I'll go to the PSA, the Philosophy of Science Association meetings. I'm rubbing shoulders with other philosophers of science. I'm not rubbing shoulders with biologists, by and large, or sociologists, by and large. Okay. This meeting's interesting. This is sort of, we have multidisciplinary perspective, but by and large, what we have today are very segregated disciplines that are segregated, right? Back in the 17th century and into the 18th century, it was truly multidisciplinary. So you would have the biologists in the same room as the physicists, in the same room as the literary scholars, and so on. The arts and belles-lettres were included. In fact, one of the characters that we'll look at was Jean de Rome d'Alembert, who was the co-author with Diderot on the Encyclopedia. And so there was even a movement in the Paris Academy to call it the Paris Academy of Sciences and Belles-Lettres. So it was truly a mix of people. As I said, it was the start of what we might think of as knowledge transfer. That's the buzzword. I don't know if it's the buzzword in your locations, but in Canada right now, everyone's talking about knowledge transfer. And we do this through journal publications, meetings such as this, and so on. Interestingly enough, the academies of this time were also entrusted with the pursuit of knowledge. So they would have prizes or awards, and here are the ones that actually interface with the little scenario I'm going to talk about. The solution to the Jupiter-Saturn problem. There was a prize for that. Right? It turns out Jupiter and Saturn do wonky things. Wonky is a technical term, by the way. Wonky things to their orbits. Right? So if you think of the Sun, Jupiter, Saturn, there's an issue with the orbit of Saturn. Well, an issue with the orbit of Jupiter. This is a famous problem, the problem of longitude. The Lunar Problem, which is the focus here, return of Halley's Comet, the tides, and geodesy, or the shape of the Earth. The main character in today's story was involved in the shape of the Earth, the return of Halley's Comet, the Lunar Problem, and this one. So he was actually one of the main characters in 4 of these major problems. And here's the punchline of the story. Ready? Oops, did I not get it? Oh my goodness. Oh my goodness. Oh my goodness. Let's, that's not good. Okay. Well, what you're missing here is, why can I not, yeah, I'm a Mac guy. This is this is too complicated. Oh, I could have used this. Look at that. There's a mouse with more than one button. With more than one button. So the punchline was a multi-term differential equation, and it was a very long equation. In fact, I only put part of it in my dissertation. The equation takes a page and a half to write out, and because Clairaut, the author of the equation, ran out of Greek characters, he had to start using Hebrew characters and all sorts of other characters. It was a very long equation to capture what's simply or what Newton thought was the equation for universal gravitation, an inverse square relationship. And it took a lot of work to get there. So that's the punchline. But how do you get there? Right? Here are the main characters. Some of them should be familiar to you, if not all of them. Newton, of course. Euler, probably depending on maybe on your if you have trading cards, with athletes' faces. If you have your favorite mathematicians of all time, he might have to be in the top 2, if not the top. Euler, D'Alembert, Alexis Clairaut, who's actually the hero of the story today, and Buffon. Notice that the four of them are strictly 18th century. And Newton straddles. So those are the characters. The expression in English is necessity is the mother of invention. Well, the necessity is the what? Well, these were the problems. These aren't small problems. In 1727, the 3rd edition of the Principia comes out. There are some serious problems still needing to be solved. As I said, shape of the Earth. Halley's Comet, lunar theory, the longitude. These weren't trivial problems. A bunch of us last night were looking at the night sky. And we were pointing out Jupiter and Saturn and Mars and where Venus was. And Pluto was actually out there, but that's not a naked eye object. Does anyone know what's the most difficult celestial object to position in the night sky? With accuracy? the moon. In terms of positional astronomy, the moon was a headache. It still is a headache in that sense. The moon, as it turns out, precesses 3 degrees, 3 minutes every revolution. At the end of Newton's life, this was an issue. It's not surprising that in the first half of the 18th century then, that people were questioning whether or not Newton was right or wrong. That's not the story we get, generally speaking, in the history of science. I point out here that the last Cartesian work to appear was in 1738, thereabouts. After that, Cartesian works kind of disappeared. So it took roughly the first half of the 18th century before Newton's work actually replaces Cartesian's understanding of the universe. That's roughly 3/4 of a century after the publication of the Principia. So even though I think it's probably the greatest work ever written, at the time, it took a fair bit of time before it was actually accepted. A lot less time, by the way, than Einstein's work. Sorry, a lot more time than Einstein's work. Okay? Here they are, if you want to see, if you like putting names to faces. They're all pretty smart people, so the Newton's law that bigger the hair, bigger the genius kind of applies here. Top left corner. Anyone? Euler? Yeah. Top right corner. The cutest one of the bunch. That's D'Alembert. Clairaut and Buffon, the buffoon, who looks like a buffoon in this. So these are the people involved. Okay. So let me just spend a little bit of time here talking about the lunar problem. Here's what, if you were an astronomer of the 18th century, you would have inherited the following. At the time, there were roughly 18 bodies in the solar system. That's it. Okay? And if you know their positions at any one time, to deduce from their mutual gravitation by process of mathematical calculation their positions and motions at any other time. Let me remind you that by the 18th century, if you agreed with Newton, two mutually gravitating, one could say they're in mutual agreement, spheres was adequately solved. They move with respect to each other based on an inverse square relationship. And so we have something like this. Anyone recognize this? This is Kepler's law, or Kepler's theorem. Notice that that black object is sweeping out equal areas in equal time. Right? So we knew that if you have two bodies, so the black thing going around some center of mass, that they will behave with respect to one another in such a way that it's fairly well determined. If I know the mass of the central body, I could accurately and deterministically tell you where the revolving body will be. And Newton shows that it would have to fit some conic section, be it a circle, an ellipse, a parabola, and so on. Right? In this case, we're just looking at an ellipse. Okay, so that's two bodies. We can understand how two bodies interact with each other and understand it. Not only understand it, we know it deterministically. Each body in our solar system can be thought of as moving nearly an ellipse or circle or something like that, a conic section around some body, but as slightly disturbed by the action of other bodies. So the problem in the solar system now isn't that we don't just have two bodies. We have this large body here, we have other ones around, and if we want to just look at the relationship of one to another, that's fine. But what happens if we introduce a mass that is sufficient and significant to disturb this body? What happens then? And this was the problem. This was exactly the problem. Given at any time the positions and motions of three mutually gravitating bodies to determine their positions and motions at other times. Right? So notice how this is changed from here, right? From their mutual gravitation to bodies by a process of mathematical calculation, their positions and motions at any other time, to three or more. Right? Turns out this isn't a simple problem. It's still not a simple problem. The problem, though, the scientists of the time thought could be simplified. If we think of the Earth, Moon, Sun trio, we could always assume that one of the three bodies can always be regarded as exercising only a small influence on the relative motion of the other two. In our case, the Moon exercises a small influence on the Sun, a small influence on the Earth, and an even smaller influence on the Sun, right? And the problem can be simplified by the fact that the eccentricities and inclinations of the orbits of the planets and satellites are small quantities. So by and large, they're all in the same plane with some small deviations. And the eccentricities outside of planets like Mars, the eccentricities of the orbits weren't sufficient to cause that much of a disturbance. So that image that I showed you of the a body or going around in an ellipse with spanning equal areas and equal times, that could approximate a circle. Okay. So these were ways of simplifying the problem. So let's go back and look at the Sun, Earth, and Moon. The Sun is obviously the disturbing body here. The Earth is a disturbing body on the Moon, and vice versa to some degree. In the case of the Sun and two planets, say Jupiter and Saturn, the Sun is still the disturbing body. However, in the case of Jupiter and Saturn, Jupiter is huge, and so is Saturn, but Jupiter exerts a huge effect on all right. So this is what happens. This is exactly what happens to the lunar orbit. So look at the Moon going around the Earth. It sweeps around the Earth in an ellipse. And if you think of the ellipse, the major axis of the ellipse, so the long axis, what's happening is it looks like that axis is moving. Okay? The Moon is trying to go in a perfect ellipse around the Earth, but every time she goes around the Earth, the whole Earth-Moon system is being disturbed by the pull of the Sun. And so the disturbing element of the Sun, or the perturbation caused by the Sun, causes the Moon's major axis of the ellipse to precess 3 degrees 3 minutes. Is that clear? Everyone's got that? Okay. A side note. When we're talking about history of astronomy, history of physics, it sometimes helps to remind ourselves that we're actually, generally speaking, if we think about people like Kepler and so on, they're talking about idealized orbits, in Kepler's case. Why do we say that? Well, it turns out, look at the moon, look at the Earth. Nothing actually ever completes an ellipse. Yet we say that the planets orbit the sun in ellipses, when counterfactually, that's not the case. Right? Now we see scientists saying, okay, well, if it's not the case, can we mathematically calculate what this looks like? So, in the early part of the 18th century, the British Parliament, through the Royal Society, offered to award a handsome prize for a procedure that would give accurate longitudes at sea. Why was this an issue? Well, it turns out there were a lot of people going on big ships and not returning. And they weren't returning because they were crashing into places like Ireland when they weren't expecting Ireland to be in that place. Right? Latitude is easy to get. Longitude wasn't. And so in 1714, early part of the 18th century, here was the prize. If you can come up with a procedure that was within a quarter degree, that produced results within a quarter degree, you got £20,000. Within plus or minus a half degree, £10,000. Sorry, £30,000 for plus or minus a quarter degree, £20,000 to plus or minus half degree, and £10,000 to within a degree. Huygens wrote a report about an expedition that went to India and was returning, expedition sponsored by the Royal Dutch Shell Company. And they lost 250 sailors because it crashed into Ireland. Right? So I have a translation of this. So necessity. So there's not only from the knowledge of and scientific perspective getting a solution, this was actually starting to have political and economic repercussions. So getting this right was important. By the mid-18th century, the Paris Academy offered a prize for a theory about Saturn and Jupiter. And there were a whole bunch of other prizes. In Paris Academy, the Berlin Academy, they would alter their prizes. One year it would be physics, astronomy. Another year it would be chemistry, biology. So they would alternate between disciplines. So there were all sorts of prizes at this time. In the 1740s, we see Euler, Clairaut, and D'Alembert undertaking a lot of work to come up with expressions for the moon's motion. Okay. Euler, in a paper, he wrote many of his papers in French, as it turns out. So this paper was Recherche sur le mouvement des corps célestes en général. Right? And he presented this to the Berlin Academy of Sciences in 1747. Here he called into question the accuracy of the inverse square law. He expressed grave doubts, actually, about that they followed the inverse square law exactly. Okay, so two bodies affect each other in proportion, inversely proportional to the distance squared between them. That's the inverse square law. If the moon isn't following a precise inverse square pattern with respect to its motion around the Earth, then what could be causing that? Could it be other terms? Maybe it's not just inverse square. Could it be an inverse to some other power, 2.143? Could it be other forces? Maybe gravitation isn't as universal as Newton claimed? What could this be? These were the questions. There were also anomalies, as I said, between Jupiter and Saturn. The other factor that comes into play here is that observational astronomy was getting better and better and better. So the perturbations were starting to appear all over the place. The moon was the big one, but Mercury, people were starting to observe the perihelion of the shift in the perihelion of Mercury, Saturn, Jupiter, Mars. That led Euler to make the following claim. All these reasons joined together appear therefore to prove invincibly that the centripetal forces which one conceives to apply in the heavens do not follow exactly the law established by Newton. The theory of astronomy is therefore still much further removed from the degree of perfection. And this is the crucial part, that the forces by which a planet is solicited being known, the motion of this planet is determined. In other words, there's a commitment here to prediction, to determination, and the thought that an inverse square law wasn't delivering positional astronomy with perfection was troubling. When Euler wrote that and submitted it to the Paris Academy for the prize for the Saturn-Jupiter, guess who the judges were? D'Alembert and Clairaut. They saw Euler's paper and began what one might call an early collaboration among scholars. Even before reading Euler's essay, Clairaut maintained that his discovery of the motion of the lunar apogee was sufficiently important to be publicly discussed at the mid-November meeting of the Paris Academy in 1747. Now, I just want to pause here for a moment. By this point, Clairaut and Maupertuis, another important figure in the Paris Academy, had already solved the problem of the shape of the Earth. By 1739, Maupertuis went to Lapland in the Arctic Circle. Clairaut actually sailed with Picard to Peru. Right? They each took a second pendulum with them, and they measured the length of the second pendulum in Peru and in the Arctic. Discovered that the shape of the Earth was actually an oblate spheroid. The Earth was squished at the poles. By this point, Clairaut had already predicted the return of Halley's Comet. So already he's delivering on Newton's program. But in 1747, the staunchest of Newtonians gets up in a meeting such as this and says, Newton's theory is false. Could this mean a revival of Cartesianism? D'Alembert supported Clairaut at this point. So now, late 1740s, we have three of the biggest names in mathematics and astronomy, all in agreement regarding the veracity of Newton's theory. Does this count as a crisis in science? I don't know. I don't think so, actually. I think this counts as science. So the Bernoullis, right, and others were ecstatic. Right? This meant that maybe Descartes was right. I think I'll skip this. This is just going into D'Alembert and politics. We've had enough of politics, right? Yeah, let's move on. So let's come back to the problem here. Buffon, who was a naturalist, but also a bit of a Newtonian, he attacked Clairaut right after Clairaut stood up and said, no, Newton is wrong. Clairaut suggested that maybe the force isn't just inverse square, but had some other terms. Right? And depending on the three bodies involved, this term here might be important or it may not be. Right? So at long distances, that second term wouldn't matter. Buffon insisted that the law of gravitation must have only one term. So here again is an allegiance to some principle. There's that M word again, right? Otherwise, it would not be a simple function of the distance and would represent several forces rather than a single force. There might be other forces at play if we had multiple terms. Well, Clairaut at the meeting accused him of being a buffoon, playing on his name. Buffon, buffoon. So these meetings got heated at times. But Buffon was actually defending an inverse square. Maybe for the wrong reasons, but he was trying to defend inverse square. And he was doing it on metaphysical grounds, as I pointed out. Whereas Clairaut was actually trying to tease out the nature of the forces that were involved in three or more bodies. And Clairaut was adamant that he was trying to do it without other physical principles besides gravitation. So he was actually trying to use gravitation in the analysis rather than Buffon's suggestion. Right? D'Alembert says, near the end of 1748, August, he says, although this proves that there is another force besides that of gravitation which acts on the moon, it seems to me that the theory of the moon, such as it is the most victorious proof of the Newtonian system of attraction. Huh. 2 weeks after, he stood up in the Paris Academy and said, Newton is wrong. Clairaut, a couple months after that, he says Newton is right is correct all along. The point here is that the analysis was difficult. And we see in this period the scientists actively working on trying to improve their results. An interesting sidebar is the attack on Buffon. We're going to try to improve the accuracy of our results based on the principles of science, not on metaphysical commitments. 1. You might be asking yourself, well, why did it take so long? History of math. It turns out that the Leibnizian use of differentials, partial differentials, versus the dot notation that the British were using, until we started using partial differential equations, they couldn't solve this problem. So this is also a case where Leibnizian methods overcame British methods. I could have spent all this time trying to work through the equations themselves. And generally, that's what we might do in a discussion like this. But I want to give you an overview of the back and forth that was going on. We might want to spend time looking at the equations and making sure we get the science correct. I remember presenting once on Newton, and the late Art Stinner stood up and said I had something wrong in my equation. Right? Fair enough. That's important. Right? But we gloss over cases like this where we actually see the scientists at work. So it means getting the historical facts, be them, the analysis of equations, analysis of text, and so on. It's important to get that correctly, but the dynamics of the stories are often treated as incidental. What I think Clairaut and others teach us, though, is how scientists engage with the work. If it's to be done well. The response to anti-vaccinations or anti-vaxxers, flat earthers, and so on, anti-evolutionary, is not simply to be doxastic and say, science says this. That's actually not the answer. The history of science, and this Clairaut incident is just one small example, is full of examples where disagreement and argument is essential for the progress of science. So what I want to leave you with is the idea that if science is to progress, it can't progress without disagreement. It can't progress without argument. And from my perspective, I think we fail to teach that. We really fail at teaching that. So to wax poetic, nature and nature's laws lay hid in the night. God said, let Newton be, and all was light. Except that the light flickers now and then. So we use the poem to talk about Newton. I've stood up and said this a lot about Newton. He's my hero. But it hasn't been all light. Right? The light flickers. And I think that's what we need to talk about in history of science. We need to talk more about when the lights go off. And I think that might help us teach nature of science. Those might be interesting stories, and so on. Thank you.
Okay, now we start the question section. Okay, go out.
So, when the French academicians accuse Newton of being wrong, they might characterize that in one of two ways. One is that his fundamental inverse square law itself is wrong, and the Buffon equation clearly adds another part of the formula that says, I think there is another part to this. The other would be, particularly when you talk about three bodies, is that the two-body characterization is simply incomplete and will appear wrong if you don't take into account other factors which involve the third body. So how much of the criticism was based solely on, like Buffon, the formula, and how much was based on, well, that may be true, but we don't have two bodies, we have 3, 4, 7, 8. And when you take the others into account, then his simple version is wrong by being incomplete rather than strictly wrong.
Right. So, interestingly enough, a few things in response. At the time, I haven't seen any characterizations as saying Newton is wrong and look, a Cartesian plenum with vortices is the way to go. So no one was doing that. In fact, what people were doing, and I'll return to Euler to answer this, if you have a chance, read Euler's Letters to a Young Princess. It's a wonderful. It's 2 or 3 volumes. It's quite accessible, where he tries to explain natural philosophy to a young princess, Princess Danho. And there he says, this is around the same time, 1738, I think, is when it was published. He says, look, if you're in England, you're going to think of gravity as an attraction, right? If you are on the continent, it's a repulsion, right? And he said, on the continent, we're going to be committed to this idea that we have to have mechanical forces. He says, what we know is that universal gravitation is correct, but to the question is whether or not it's an attractive force or a repulsive force hasn't been decided and can't be decided. Right? I think that's an interesting comment to make. He's pointing out that we know the physics of it is correct. The metaphysical underpinnings is what we don't know. This is essentially what he's saying, right? So he's committed to gravitation as inverse square. In the Paris Academy, that debate of whether or not it was attraction at a distance or repulsion was motivating the arguments against Newton, right? Yet Euler was saying, no, bracket that stuff off, right? The third thing is they didn't know. They simply didn't know, because it was there was one metaphysical attachment. The attachment was to get precision and determination in the equations. No one knew how to do things by approximation. The thought of a law functioning by approximation at the time was anathema to them. So naturally, they were searching for other components of the force. Could it be other forces? Perhaps. But if it was other forces, then it wouldn't be universal gravitation. Right? So it was. I think it was a period of confusion in the end.
Could you elaborate on the how Euler's paper was presented, whether it received the prize, and was it read, and was it discussed, or was it kept secret, and just Clairaut and D'Alembert are interacting with it? And another question I have is, you described that Clairaut made that statement that Newton is wrong, and then 2 weeks later he has changed his position, but I didn't quite follow what changed or what was going on in Clairaut's thinking and analysis in that revision of what he was willing to say.
Good questions. The first one, Euler's paper wasn't kept secret. It was actually published. He had over 80 books published in his life, and countless, I forget the number of hundreds of papers. And his book on algebra was still being used not long ago. It was that good. That's Euler. So it was published. And at the same time, he also claimed part of the prize for the longitude problem. He did some work with Tobias Meyer, who claimed, I think, 10,000 pounds of that prize. But we know Harrison and the Harrison clock was eventually what won that. So thank you for the question, because it didn't come out clearly in the presentation that the publications, another reason why this is important is that the publications and the public presentations of the results sped up knowledge transfer. So this is actually quite huge. Okay, so that's one. Now the second question about Clairaut. That scenario is better understood when you think about the return of Halley's Comet. So if Newton's theory was correct, and that this comet had an orbit that was super elongated, and if it was to return, it should return by a certain time, right? And provide, as long as the comet isn't interacted or interfered by some larger body, it's going to be essentially a two-body problem and could be solved deterministically. Except that for Halley's Comet to return, it may have to go by Jupiter, Saturn, perhaps even the collective mass of all the planets might disturb its orbit. So that turned out to be an n-body problem as well. So Clairaut was working on this at the same time as this problem, and what he discovered was this long equation to which I've been alluding required a lot of calculation. Interesting sidebar. Calculators. Right? We're women. And so the solution to Halley's Comet was actually a solution that required and depended on the mathematical skills of calculators. And not mechanical calculators, but people, women calculators, who were carrying out these intricate calculations. So that was part of the story that I left out. And so the retraction, the public retraction, was actually as a result of fine-tuning not only the equation, but some of the calculations that went into place. Okay? Just so that I'm not misunderstood, when Newton died, and he said the moon was his biggest headache, in the Principia, he accounts for half of the precession, the 3 degrees 3 minutes. And he makes some offhanded comment in the Principia that says, something to the effect, well, here's half of it, the other half is obvious. It's obvious that the other half is there, right? It's led a number of people, including someone like Richard Westphal, to accuse him of an academic crime. I forget what he called it, right? Fudging the results. That's what he called it. and that was a sentiment that was sort of floating around here. Right? You know, you didn't quite get it all. And here's the closest body to us, and yet we don't have it accurately. Clairaut's work helped to dissipate that. But it wasn't a simple dissipation. It was actually a complex dissipation. It took a few weeks more of calculations before he got up and said, you know what, I think we have this right. And I think he did it to 4 terms and realized that, you know, as he did more and more calculations, he was recovering more and more of this lost perturbation, right? So that's really what motivated it. So I'm not sure I answered the question, but the answer is the calculations, but also that there were other historical events going on that could have come into the story that I excluded. Yeah.
Okay, we're going to the next conference now.
Thank you.
Thank you, Professor.